So I'm going to give an introduction to GPU programming using a Python library called Theano. So first I'll just talk a little bit about myself. Currently I'm working for a company called Zalando. They're a German online retailer. They just set up in Dublin a few months ago. I'm there about 2 months and we're hiring at the moment. So I've been using Python for about 5 or 6 years in different domains, web space, web applications, machine learning, stuff like that. And I just really like Theano and I think it's cool. So that's why I give it a talk on it. If you're interested to know about what I'm up to on Twitter or stuff like that, just go to my About Me page. Some other details there as well. Okay, so this is what I'm going to talk about today. First, I'll just overview a quick overview on matrix computations and linear algebra. Then I'll just introduce Numpy and Theano. Then I'll discuss the advantages of Theano and some of the components, which include tensors and the symbolic differentiation feature of Theano. And then I'll finish off with a couple of examples. First example will be a simple machine learning linear regression example. And then I'll finish off with a matrix factorization example. So, just in case you're not familiar with linear systems appear in many different areas of engineering and science. They appear in signal processing, machine learning, deep learning. Theano is used a lot in deep learning. So they appear a lot in science and engineering. And efficient routines to solve computations and perform computations on matrices are really required for the problems. So that's why we spend a lot of effort, applying these computations in GPUs and stuff like that. Okay, so what is a linear system? So you might remember this from school or high school, where you have a matrix. This is our matrix here, matrix A. It's a square matrix. It's something similar to an array in computer programming. And we have 2 vectors, B and X. And so I'll be using this as kind of the basis for the examples throughout the talk. Okay, so just to recap on what matrix multiplication is. So Theano and Numpy and these tools, they're efficient at performing these computations. So I'll just explain what those computations involve. So here we have we have a matrix, a tree matrix A, and we have a vector X. And a matrix multiplication is different to say, standard multiplication in a number of ways. So here we have a matrix A, and each row of A is multiplied by each column of the vector beside it, or the matrix. So here we have our rows. And each one, as we can see on the right-hand side there, is multiplied by the vector, and those multiplications are added together. So for a 3 by 3 matrix multiplied by a 3 by 1 vector, you end up with a 3 by 1 vector. So as these vectors and matrices become large, the number of computations involved on the right side here grows quite a lot. So for an m by p matrix, I have A is m by p, and for another vector, p by n, the number of computations involved is mnp. So here we have a 3 by 3 multiplied by 3 by 1, and that gives us 9 computations here, 9 multiplications. Okay, so how do we usually do linear algebra on Python? So as most of you probably already know, we use Numpy. So Numpy is the fundamental scientific computing package for Python. It's used extensively in science and engineering, and it comes with a number of different routines for solving different problems like linear algebra, which we'll discuss. It has routines for Fourier transforms and has routines for random number generation. Okay, and the main feature of Numpy is all these operations are done on an ND array, which is basically a C-type array. So we have contiguous blocks of memory where the data is stored in that memory, and basically it's a C-type array operation. Okay, so here we have a simple Numpy. So there'll be a lot of code in this presentation. Most slides will have some sort of code explaining the examples. So here we have a simple linear system of equations, similar to what we've seen before. We have some values here, and we want to find the solution, the values of x0 and x1. So the standard NumPy way of doing that is just to import NumPy, set up your arrays, and then you solve by using a standard routine, the solve routine. You can see the result here on the next line is just the expected result. And the type of the X is n in the array as discussed before. So when it comes to large matrices, I'll just provide a simple example here. So all these experiments have been run on an Amazon EC2 GPU instance. So it's quite fast, and obviously has a GPU, and that'll be used in the GPU experiments. So here we have two matrices, A and B. I just perform a simple element-wise matrix multiplication, and we can see that performs pretty quickly. I then perform a matrix multiplication, similar to the example I showed previously, and we can see it takes a bit of time, 40 seconds. The size of these matrices are up around 800 megabytes. And also the type is a float 32. That's required at the moment. I think Theano only supports a float size of 32. Okay, so Theano. It's very different to NumPy. So we've been discussing NumPy, and you're probably familiar with NumPy. Theano performs similar operations, but in a very different way. So Theano obviously will have speed optimizations due to the fact that so Theano, the computations are expressed in a computation graph, and parts of those computations are compiled to CUDA. So in the background, when you set up your Theano model and you go to solve that, in the background there's some CUDA routines which are used to implement your problem. Those routines are then, so the function that Theano actually creates, that will give you a Python callable object. So when you're using Theano, this won't be obvious to you, but just keep in mind in the background, these computations are not being run in an interpreter or in an external C library. It's being run directly on a GPU instance. So one of the main features, I suppose, themes of Theano is that the setup for our computations are done in a symbolic way, which I'll show in a few examples. And because we're doing things in a symbolic way, we can then exploit things like symbolic differentiation. So in machine learning and in deep learning and in optimization, differentiation and calculating the gradients of functions is a very common problem that you run into. Typically, you'd have your function and you'd derive it yourself analytically. But there's a feature of Theano that will allow you to just specify the function, and it will come up with the symbolic differentiation for it. So if you're familiar with SymPy, which is another symbolic programming language, is basically like a computer algebraic system. Theano is in some ways similar to this. Okay, so another advantage is that because things are symbolic, as I mentioned, it will reduce expressions down into more sensible forms. And if it identifies that there may be numerical issues with the expression that you've inputted into the system, it will try to optimize that for you to avoid those situations. Okay, so as I said, Theano is mainly used in deep learning. So in deep learning, you have large neural network systems. So the weights in neural networks can be modeled as matrices, so it's basically the same problem or a similar problem. And deep learning is used extensively in that domain. Okay, so this is our first Theano example. So we just import Theano. So when you import Theano, and if there is actually a GPU grid on the machine, it will actually echo the model of that GPU device. So at this point, you'll actually know that Theano will target your problems through the GPU. If this doesn't come up and you're playing around with Theano you may, the computations will still run, but they'll be targeted to the CPU. So just keep your eye out for this actual echo message on the actual import. So the first step is to set up your symbolic variables. So for this example, like the previous example I had where we had the random matrices that we multiply with here, we're going to set up two symbolic matrices. And this is how you do that here. So I've got two matrices, A and B. The type of the matrix is a tensor type. So this is basically the type that Theano uses for representing data. And it's something similar to the ND array in Numpy, but it's a symbolic variable. We then go on to define the model or define the function. And we perform the same operation as we did previously, just a dot product between two matrices. And just to show that there's no computation done here at this point, I just print out y, and it just demonstrates, just gives the actual operation that will be performed when it's used in Theano. Okay, so this is the main part. Once we've set up our model and our inputs to the model, we can then use the Theano function routine to actually create the multiply function on the fly. So this is where the compiling goes on in the background, and you're presented with a Python object that you can use to access that code. So it's like a C extension. So just demonstrate that here. And so I run the same example as I did previously, where we multiply A by B, and this time it runs in 6.6 seconds. So the original Numpy operation that was run on the CPU took 41 seconds, and we can see that the Theano GPU implementation runs an awful lot quicker. So you can see the advantage there why you'd use Theano. Also, I must mention for the Numpy experiments, we were utilizing all 8 CPUs on the instance. So it was pretty optimized NumPy, and that took 41 seconds, and Theano on the GPU took a fraction of that. Actually, there was a speed up of 6.2. Okay, so as I mentioned, Theano implements symbolic calculations using tensors. So in the same way in NumPy, where you have a number of operations that you can perform on a matrix, similar operations exist for the tensors in Theano, so you can perform the same operations. Also, so the examples I've shown were just purely symbolic tensors. It's possible to actually initialize a tensor with an ND array, which is a NumPy ND array. Actually, I probably haven't mentioned that a tensor is the same as a matrix. It's just a large dimensional matrix, so a 3-dimensional matrix is a tensor. Okay, so yeah, we have this feature where we can share the data in tensors, and these tensors can then be shared between different functions. So that allows us to hold internal state for like machine learning systems, neural networks and stuff like that. Okay, so here's an example of some tensor operations. So I'll just run through this quickly because I want to get through the examples. So we have our ND array set up here. It's just a 3x3x3 matrix, where the first facing matrix is set to 0, second facing is 1, and the third is 2. We perform a mean operation on that, and we get our array output. I do a similar thing with Theano, this time using a symbolic tensor, just a standard tensor. I set up the function. It's a little bit, the syntax is a bit different, and we get the same result. Also, just to illustrate the shared tensors, perform a similar thing where we have our Theano shared on A. So this references the previous A, and we set up our model here. We can see here that the model actually references C directly, and when it comes to actually specifying the input to the Theano function, no inputs are required, so we can see that there's internal state being saved here. Okay, so as I mentioned, differentiation is important in machine learning and optimization. I'm going to give a couple of examples of how Theano helps you here. So differentiation is just a rate change of a function. The function, the Theano function used to implement that is just t.grad. So there's extensive support for partial derivatives and matrices of partial derivatives in Theano. So Jacobian and Hessian matrices appear frequently in machine learning, and the support for all that stuff. And so I'm going to take the simplest example possible and just demonstrate the derivative of x squared. Okay, so I'm going to import a pretty print function from Theano just to make the output a bit prettier. So I set up x. Our model y is just x squared, which was on the previous slide. And then pretty print the output, and Theano will show you symbolically what the model y looks like. Here I calculate the gradient. Well, actually, I set up the gradient. Nothing is calculated at this point. And Theano will give you a kind of a verbose, unoptimized output for that gradient. At this point, we set up our Theano function, f, and we do a pretty print on the output and look at what the symbolic result of the differentiation is. And you can see it's 2x, which is what our expected output is. So we have f set up, it's all symbolic, and we provide a value 4, this is a scalar value, and it produces the correct value 8. So as simple as that. So these operations can also be done element-wise on matrices. So just similar to the first example, the previous example, I have x set up here as a matrix, and basically go through the steps again, set up the Theano function, and at this time I input a matrix to f. And it gives a matrix output. So each element of f has gone through the 2x function. Okay, so I'll just discuss, we'll present a simple linear regression example. So if you've seen or used machine learning before, you've seen these examples. So this is just a linear cloud of data. The challenge is to fit a line that best models that data. So some sort of line through the middle there. And this is our cost function. So for optimization, you usually have a cost function, which is this was the original data and our model. And then using a gradient, we use this cost function. We take the gradient and we use it with a machine learning technique called gradient descent. And we find the optimal value or the optimal line through the data here. Okay, so the example here, I just set up some test data, which is the data cloud I've seen. I set up some our symbolic variables. I define the model. I then set up the Theano function and execute the model. And I just set up the Theano. I was setting up the model parameters here and the model. Then I set up the cost function, which was the expression on the previous slide, and I set up an expression for the gradient. And this is an update for the gradient descent. So I input all that data, all those variables into the train function, and I train over 100 iterations. And when that stops, I look at the model value. So this is a shared, because this is a shared tensor, I can actually pull values from that using this function here. And this is the slope of the line through the data according to the training algorithm. So just to plot the results, we can see here, this is the result from Theano, and it just goes straight here. So this is just a simple tie example. So Theano is really for like high speed computations, and you may not necessarily need that for an example like this, but just to demonstrate how the symbolic differentiation works and how the Theano function can actually implement linear regression. Okay, so I'm going to discuss a more complicated example called non-negative matrix factorization. So this is basically we have one matrix, and we want to split it into two matrices. Okay, we have an added constraint on this problem where x is non-negative. That means has no negative values, and we also want w and h to be non-negative. Also, this is a dimensionality reduction technique, so the w and h won't be square, and so this would be like m by n. This is the input. Then w and h would be like m by r, so it's lower rank. So yeah, just to illustrate the additional constraint, w and h have to be non-negative for this problem. So we're going to use the same least squares cost function, but the actual additional constraint really changes things. So non-negative matrix factorization is used a lot actually in machine learning for different types of problems. So we have two things that we need to find. We have updates. We need to have updates for both. And this is what the updates look like. So the reason why I took this example was because it's all matrices based, and you can see that we're using matrix multiplications, and we also do some element-wise divisions and some element-wise matrix multiplications as well. So, okay, this is an example that I actually forked from GitHub, and it's an implementation of NMF. Implementation of NMF for in Numpy, pure Numpy. In Theano with the pure symbolic tensors, and another implementation, so there's three implementations, and the third implementation uses shared tensors. So I'll just briefly go through this here, so it's quite long. One thing I should have mentioned earlier in my earlier slides, for the random number matrices I generated, you wouldn't typically generate them that way for Theano. Theano has some nice random number generators, and if you need to generate random numbers, this is the way to do it. Don't use Numpy for that. Okay, so here in the NMF routine, we take our inputs x, the matrix we work on to factorize, r, which is the number of latent features, and the number of iterations for the algorithm. So here we have our Numpy, our Numpy implementation of our two updates, and it's all pure Numpy. On the second implementation, we used the shared tensors. So the matrices W and H are initialized randomly. That's why the random routines are in there. So we use shared tensors here to implement algorithm. And they're inputted to our Theano function like this as an update. There's no input or output model here. And then on the third example, we're using pure tensors, matrix tensors here. We set up some update rules and a cost function, and they're inputted into the Theano function. And this is also run for the same number of iterations. Okay, so this is a script. The script will run the three routines for the same input parameters, and will provide a timing output so we can compare the three. Okay, so yeah, as I mentioned before, this is on a GPU AWS EC2 instance. It's NVIDIA Grid card, which has 1,536 cores, 4 gig of RAM, and this is just one instance, one example of the script being run from command line. I ran the script for a number of times, and I've tabulated some results here. So this is the size of the matrix, n. So in this example, we're creating a random matrix of size 4,000 by 4,000. It's run using the three routines, and we can see the time it took to perform each factorization in seconds here. You can see it took Numpy 22, and Theano was like a fraction, it's only like 2, so 10 times improvement. So as we go through the experiments here, I double the size of the matrix, and observe the output of the performance for each routine, and we can see that Theano is pretty fast. So for the biggest case here, you're looking at 340 seconds, and here's like 25 seconds. You can also see that for the shared tensors, that's a bit slower. There's overhead involved in shuffling memory around and stuff like that. But for the pure symbolic implementation, which the GPU is optimized for, we get some nice performance results. Okay, so I'll finish. Okay, so we discussed Theano with some simple matrix computations, and we compared that to Numpy. Demonstrated the symbolic differentiation stuff using a linear regression example. We had a look at implementing NMF, non-negative matrix factorization. And yeah, the experiment showed that the symbolic tensors perform better symbolic tensor implementation performs better than the shared tensor implementation. Okay, so just finally, finish, so there's loads of really nice resources for Theano. So this talk is very much an introductory talk, just kind of get the idea out there and get people, make people aware of it. But there's extensive documentation, which you can find on the web, and also some really nice talks. And this is particularly one talk that I really like. It's kind of a high level. It's kind of a high level talk. It deals a lot with convolutional deep learning nets and stuff like that. But I recommend you look at that as well. Okay, thanks.